I am going to continue my video series on the characteristic of nonparametric methods by discussing some of the issues associated with discrete statistics and exact tests. That is, what are some of the issues that arise when we account for the reality of measurement? Even when we assume an underlying continuous construct, we never measure on a continuous scale. Our measures are always discrete, and this leads to some considerations that I'll discuss now. To do so, I'm going to use the same small set of data that I've used in previous video series when I've exemplified some of the nonparametric methods: 3, -2, 7, 6, -1, and 12. If you watch the series on randomization test, you know that we can do a randomization test with these original scores. Here I'm showing you just a small part of the probability distribution when we use these scores and do a randomization test. Namely, I'm showing you the upper tail of the distribution. The value t stands for the test statistic, and I'm providing the largest possible values of the test statistic that we can have with these data, as well as the probability of obtaining that value of the test statistic or higher. So this is the upper tail of our distribution. We could also rank these scores, ignoring the sign of the scores, ranking with respect to the absolute value, and use the Wilcoxon signed ranks test. And here I'm giving you the distribution for that method. This is a randomization test with ranks. Again, t is the test statistic. I'm showing you the largest possible values of that test statistic when we have 6 observations, and I'm showing you the probability of obtaining that test statistic or an even higher value. The first thing we notice now that I also brought to your attention in previous videos is that unlike when we use parametric methods, we have jumps in these probabilities. When we use parametric methods, we do not, because we're using a mathematical model that is continuous as a model of our data distribution. The reality, of course, is we have discrete measurement, and therefore whether you're using a mathematical model that is continuous or not, with the observations that you have in hand, there are only certain probabilities associated with that distribution that you are going to encounter. That is because you measure discretely, regardless of whether or not you're using a continuous model. Now, I have heard some people say that they're not sure that is true, because when you're using, for example, the mean and the t-test, you're calculating a mean of your observations, and the mean of those observations may very likely have decimal values, making it appear as though you're using continuous values. That's not true, and I can prove it to you. Think about the randomization test with original scores. How did we obtain the value of t? We obtained the value of t by summing up the positive ranks. Now let's look at the formula for the mean. What is in the numerator of that fraction? It is the sum of scores. And notice we're dividing by a constant, the number of observations. If I was to use the means in a randomization test, something interesting will happen. I will get the same probability distribution that I obtain when I do a randomization test with the original scores, just using the sum of scores for my test statistic. The fact that you have decimal values as possibilities does not mean that you now have a continuous statistic. You only have a discrete number of means possible, and those possibilities are going to be defined by whether the participant in the treatment condition or the control condition did better. That is, whether your difference score is positive or negative, that's what's going to influence what the mean's going to be. The number of possible means that you can obtain is the same as the number of permutations that you can obtain when you do a randomization test with scores or ranks or any replacement score. Having a number of decimal values does not give you continuous data. Another issue that you may need to tend to when you're dealing with discrete data using a randomization test has to do with the fact that we assume an underlying continuity to our construct. In theory, if you have continuity in your construct, you will never end up with ties in your data. The reality, however, is that you're measuring discretely, and so it's very possible to end up with ties in the data. In the world of nonparametrics, there's a lot of discussion about the different ways to deal with ties, and I believe that many of those discussions are much ado about nothing. Let me show you what I mean. Let's suppose that I want to use the Wilcoxon signed ranks test with these scores. Looking at the absolute value of the scores, The ranks are these. The -1 is associated with a 1. The -2 is associated with a rank of 2. The 3 is associated with a 3. The 6 is associated with the rank of 4. The 7 with the rank of 5. And the 12 with the rank of 6. Here again is the upper tail of our probability distribution, showing you the highest possible values of the test statistic, as well as the probability of obtaining each of those values or greater. A lot of what you may read when you learn about how to deal with ties with this particular test involves making adjustments to a formula. Those adjustments are designed to give you an approximation, but they're not needed. What you can do instead is conduct an exact test even if you have ties in your data. Consider that in our set of observations that 7 had been a 6, so that now we have 2 6s. Again, let's rank the data. The -1 is a 1, the -2 is a 2. Remember, we're ranking without regard to the negative sign. The 3 is a 3. Now what are we going to do about the 2 6s? When it was a 6 and a 7, we had a 4 and a 5. We're still going to use a 4 and a 5, but since both values are 6, we're going to average those. That is called a mid-rank. We're going to give both 6s a mid-rank of 4.5, then we're going to give a 12 a 6, and now we're going to do a randomization test, and what happens is we end up with a different probability table. Much of the table looks the same as it did before, but notice the test statistic with a value of 17. When we did not have ties, we had 0.109375. When we do have ties, we have 0.093750. So the probability has changed, but it is still an exact probability, this time an exact probability based upon the fact that we had 2 ties. No formulas were needed, no adjustment was needed. What we did need is the ability to generate this table. You don't want to do it by hand, especially as the sample size grows, but in this day and age, there are software packages that will generate these probability distributions up to moderately large and even large sample sizes. So with those software packages, we can ignore calculating the formulas and making adjustments to give us approximations. We can use exact values. The fact is, when you have discrete data, if you have the computational power, you can calculate exact values. You don't need to use approximations. Now let's look again at our 2 partial probability tables, one with original scores and one with ranks. Suppose that I set my tolerance for errors at 0.05. What would be the critical value if I was using original scores? I am looking, of course, for the value in which the probability of that value or greater will not exceed 0.05. That value is 29, and the probability of 29 or greater is 0.046875. That value of 0.046875 is our probability of making a type 1 error if the null hypothesis is true, not 0.05. That's another difference between using mathematical models and using exact probability distributions. Because we are using discrete values, not all probabilities are possible, and therefore our actual type 1 error rate is very likely not going to be equal to the nominal level that we set as our tolerance for a type 1 error. I call the actual type 1 error rate alpha prime, and here it is approximately 0.047. So it is slightly less than our tolerance for errors of 0.05. Look at the randomization test with ranks. If we set alpha of 0.05, our critical value is going to be 19, and our tolerance of errors is still going to be 0.047. For both of these tests, that with original scores and that with ranks, we ended up with the same probability of a type 1 error when the null hypothesis is true. Let's now assume that our tolerance for error is 0.10. The table with original scores tells us we could use a critical value of 27. We'd actually need to know what the probability is of 26 or greater to see if that's still under 0.10, but I can assure you it is not. So we're going to take 27 or greater for our rejection region. Therefore, our alpha prime is 0.094. With ranks, the critical value is 18, and our alpha prime is no longer the same as it was with original scores. It is now 0.078. So whether we use original scores or replacement scores, we could very well end up with different actual type 1 error rates. What are the implications of these type 1 error rates? Well, you know that it is a balancing act between type 1 and type 2 errors, and if you decrease your type 1 error rate, you're increasing your type 2 error rate, that is, you're lowering your power. So there's going to be more power here with original scores than there is with ranks, all else being constant. That's a very important conditional clause I'm making here, because we should not use the differences between our actual type 1 error rates to choose a procedure. Wait until you watch the video series on relative efficiencies, and you'll recognize that there are other considerations that are more important than the actual type 1 error rates that we get because of the differences in the types of scores that we're using. But all else being constant, we would get more power here with the randomization test with original scores than we would with ranks. Again, for emphasis, the underlying distribution may affect original scores more than it does ranks or vice versa, and therefore you should not use this as your consideration in choosing a method. Now consider again our randomization test with original scores in which alpha prime is 0.094. That means that we would have roughly 91% confidence in our results. Or would we? If we set alpha to be 0.10 and alpha prime is, say, 0.09, do we have 90 or do we have 91% confidence? It is indeed fair and correct to say that you have 91% confidence. There was nothing going on behind the scenes in which you chose a method based upon your results. It just turned out that the actual type 1 error rate led to 91% confidence. But I would urge you to also consider publication realities. Readers who are not familiar with nonparametric statistics are going to understand if you said 90% confidence that you set alpha at 0.10. That may be enough justification to say that you're 90% confident rather than saying 91%, and indeed you are at least 90% confident, so that's a conservative statement. Is this another reason to consider the possibility of using mathematical models and parametric tests? Because when we say 90% confidence, we really are? No, let's look at parametric test versus exact test. Consider the match pair design with randomization. The one-sample t-test provides an approximation to the original scores randomization exact test, and the approximation improves as the number of observations increases. This is a common link among parametric and nonparametric methods with randomized designs. Nonparametric exact tests provide the standard for evaluating the closeness of the approximation. So when you use the one-sample t-test, you're approximating an exact test. The bigger your sample size, the better that approximation. And in fact, if you get a large enough sample size, we could switch to the parametric procedure for a large sample approximation, and that may be what we need to do if we hit the limit in terms of our computational power, but we do it knowing that we're now in a territory where the parametric test can give us a very nice approximation to the nonparametric test. So you can think of parametric test as providing large sample approximations to our standard that provides exact values, the nonparametric test. And in the next video, I'm going to look at large sample approximations for some of the nonparametric methods that we have learned about so far.